Good morning, and thank you for participating to this webinar. My name is Bruno Charletti. I am the product manager at Fluigent. And I will co-present with Nicolas Lafitte, which is R&D project manager. I was in charge of the development of this flow sensor. The presentation that is called Flow Sensors in Microfluidics, Challenges and New Fluigent Sensors to Address them. So here's the timeline of the presentation. So first, we will discuss why flow sensors are highly important for microfluidics and millifluidic applications. And we will discuss the main technologies that are available today on the market and what are their advantages, but also what are their limitations. I will next discuss and introduce the NIFS, which is the new non-invasive flow sensor, discussing the main specifications and features. And then Nicolas will have a focus on the development aspect that we had throughout the development, because to make this technology a unique product. And finally, we wanted to show you how the system was working in real life. So we made a video including setting up the whole system, so the whole hardware as well as the software. We'll also discuss the performance that we can see throughout the presentation. So flow sensors are a prerequisite for many microfluidic and millifluidic applications. So I guess some of you are already aware of flow rate is an important parameter when you're generating microfluidic droplets. So for instance, here you can see on the left picture that the flow rate has a direct impact on the droplet size. Regarding cell perfusion, organoids, and other life science experiments and protocols, the shear stress is directly related to the flow rate that is applied on the cells when you're making like cell perfusion. So you want to master the flow rate in order to make sure you apply the right shear stress on your cells. It is also a very nice tool for diagnostic, drug screening, and cell cytometry applications where you want to monitor the flow rate. Flow sensors are also very important if you're making a microfluidic or millifluidic protocol and you want to make sure all the flow rates are well commanded. So it's a good addition to your system in order to make sure there is no clogging or no leakage into your system with a live monitoring that allows to identify and prevent any failure during your protocol. This is actually also a very important tool for us because our whole flow control offer consists of a pressure-based flow control in which we combine pressure controllers and the flow sensors, and then we developed a feedback loop system in which we managed to perform flow rate control based on pressure. So when you're integrating or using flow sensors into your systems, there are like several aspects that you want to make sure that your flow sensor is capable of. So first, you want to make sure that the performance are good enough depending on your applications. So we are thinking about repeatability, accuracy, of course, reliability and robustness, the range of flow rates. So for instance, if you have one reference for a large range of flow rates, it's more convenient that 5 reference for 5 ranges of flow rates. Compatibility with all type of liquids, and also the type of sensor, if it's invasive or non-invasive. So if it's on the fluidic line or it's outside of the fluidic line. So of course, this is the dream flow sensor, but that's now how it works. So there are like pros and cons for all type of sensors, and of course there is no a sensor that meets all of these requirements. And of course the cost is also an important parameter to take into account when you're developing your own system. So in the microfluidic and millifluidic markets today, there are two main categories of the sensors. So we can have two main categories, which are active and passive flow sensors. In active flow sensors, an external force or external parameter is applied on your system, and it allows to measure the flow rate, which is the opposite of passive flow sensors. So as you can see here, regarding passive flow sensor, there are not many flow sensors on the market, which makes use of passive sensing. So we will mostly focus on the active flow sensors here, and mostly to two most important technologies. The first one is the calorimetric flow meter. So in these flow meters, you have generally one heater and a sensor, so usually one or two sensors. So in this sensor, for instance, heat is applied on the fluidic line, and then you have sensors on both parts of the heater. And thanks to the different differential temperature that is measured between these two sensors, one can determine the flow rate. So this is actually one of the most mature and the most widespread technology in microfluidics today. This is actually the technology we're using in our flow sensor at Fluigent. They give an overall great accuracy with 5% of accuracy with the measured value and pretty good response time. The limitation we face today with this sensor is that there are clogging issues. So depending on the sensor you are using, some of them have very narrow channels. Some of them have about 50 micrometer diameter channel. So if you're using cells, or if you're using droplets, or if there's just a little bit of dust in your system, clogging issues can happen. Also, these kinds of sensors are typically calibrated for aqueous liquids, so mostly water. And so one needs to make liquid calibration if you want to use different type of liquids. So this can be done once, but it's quite kind of tricky. And if the chemicals change within your solution, you will need to make another calibration. Of course, as it's on the fluidic line, you need to make a cleaning after an experiment. So at Fluigent, we recommend to use water, then IPA, and then air to clean the whole system. And another limitation here is that depending on the liquids you're using, this can affect the flow sensing. There's another technology which is less widespread but still used in microfluidic, which are Coriolis flow meters. So in this system, you apply a current and then a magnetic field. So there is a coupling of Lorentz forces and Coriolis forces, and thanks to that, the flow rate can be deduced out of it. So the great advantage of this system compared to the calorimetric flow sensors are that they give an excellent accuracy. So here it's more about 0.6% of the measured value, which is quite robust if you want to have a highly precise system. Response time is quite similar to the flow sensors, and we meet the same limitations that with the calorimetric flow sensor, meaning that it's still an inline flow sensor. So we have still the clogging issues, and that's the most important issue when you're using inline flow sensors. And then regarding specific limitations of the Coriolis flow sensor, it's that's the footprint, so it's more larger. It's larger than the calorimetric flow sensors, and it's also more expensive than the flow sensors. So this is why at Fluigent we wanted to, as we saw some limitations in these two types of sensor that were the most widespread, we developed a new type of sensor, which is the NIFS. So the non-invasive flow sensor, which is the first non-invasive and calibration-free flow sensor for microfluidics and millifluidic applications. So this sensor needs to be combined and coupled with Fluigent pressure-based pressure controllers in order to work. So this sensor was developed with CSEM, which is a company in Switzerland. I guess most of you are aware of this company. So it's a collaboration, a co-development with CSEM, and this is a patented technology. So regarding the key features, the flow rates that we can achieve with this sensor are ranging from 100 microliter per minute to 10 milliliter per minute, with one reference only, with an accuracy of 5% of the measured value. So it's contamination free. As you can see, it's not on the fluidic line, so you don't need to have sterility issues or cleaning. You don't have to think about cleaning your system after making an experiment. So as you can see on the working principle, so the NIFS is put on the pneumatic pass of the system. So if you're using a pressure controller, so a Fluigent pressure controller, you have a regulated pressure that comes here and then goes through the NIFS, and then it goes to the fluidic application. So you pressurize your system and then you inject, and the flow rate measurement is made at the pneumatic part and not in the fluidic part. I will explain later more into details how it works, but in short, in a few words, we're measuring the gas flow rate, and we have a completely leakage-free system. And so we can deduce the liquid flow rate out of it. So that makes this system calibration-free, and that will function with all type of liquids, as long as this is Newtonian liquids. And so you don't have to make any calibration for oil, for water, for blood, or for any kind of type of liquids. And it's plug and play, of course, so you can directly connect it to our pressure controllers. It will be recognized, and you can perform directly flow rate regulation. So it's not only a sensor; it's also allows for regulations using our complete offer. So this is how the system works. So here we combine sensors, calibrations. We have several manifolds. We have valves. Thanks to the whole of this system, we can measure the gas flow rate out of it through a mass flow rate measurement, the previous mass flow rate measurement into the sensors. And through a zero leakage system, we can deduce the volumetric fluid flow rate, because here we want to make sure that the gas flow rate is completely equal to the liquid flow rate. So for that, we need to make sure that there is no air leakage in whole the pneumatic system. So this is why we developed a zero leakage system, so that the gas flow rate equals the liquid flow rates. And then, thanks to our algorithm, we can also measure the flow rate and then perform the regulation thanks to a feedback loop system that I already introduced with our calorimetric flow sensors. So here it's the same principle, but we apply it with this type of sensor. So I will let Nicolas, which is our R&D project manager, discuss more into details on the development, what were the main challenges, why it was a demanding development, and how we managed to make from this technology a real product.
Thank you, Bruno. I hope that my microphone is working now compared to the beginning. Is okay?
Yeah, it's fine.
Thank you. So actually, this, like it was presented by Bruno, this new product has demanded a lot of innovative development and technology. So basically, we put in these slides the point we have developed in the R&D of Fluigent. So with a challenge to measure very low flow rates, it has been complicated to develop the instrumentations with a high sensitivity adapted to the microliter minute flow rate. Like it has been said, we try to address the microliter minute flow rates until the milliliter minute flow rates. For that, we have to choose and develop all the electronics and all the system inside the NIFS. For that, to get this sensitivity, we have to develop a very low noise signal in order to get this very low signals from microliter minutes. We did inside the system, we didn't develop the design and the inside of the system, but we have different and many sensor inside and many electronics, which are not flow rate sensors. So we develop a system to calibrate the physical sensing we do inside the NIFS to get the flow rate. So this is made by our test bench in Fluigent. This design is also totally temperature compensate, since the flow rate of the air is depending on the pressure and the temperature. So everything is compensated from these two physical parameters. So this is about the sensing. Also, like I think you get the point. This design is made to have no leakage. Since if we have a leakage, we will not sense the good value. So we had a very big challenge on the mechanical integrations to get low leakage, mostly under pressure, under 2 bars pressure. So it has been a big challenge for the mechanical team to have this very low leak-proof integrations of the sensor, the manifold, and the PCB. And also we ensure that we have an ergonomic solution for the customers and the setup of the customers. Then there's been a big challenge, and this is also mainly related to the regulation and the sensing part. So since air and gas are not behaving in the same manner, the dynamic are not the same for the air and the liquid. Actually, it's easier to deal with liquid than with air. Air is another fluid that is compressible, for example, and much more prone of variation of pressure. So we did have to model the model of the NIFS, the pressure controller of Fluigent, and the reservoir. We did have to understand and model these parameters and to compare in order to deduce the liquid dynamic. So we have developed, after developing this modeling of the air dynamic versus the liquid dynamic, we have developed this air gas control algorithm. This also has been a big challenge. This is one of the things we do very well in Fluigent, the algorithm, the control of the liquid and the flow rate. And so we adapted our before algorithm to this new development. And this also in a few words, just wanted to show, we wanted to show this, what can be the challenges we have faced and how we did to enhance the flow rate we show to new customers. So on the left side, you can see that the dynamic. So we compare in the slide, we compare in orange the value of the flow unit, the typical flow sensor, liquid flow sensor we sell in Fluigent, and we compare this value with the gray curve that is NIFS device value. So at the beginning, when we take only the raw data, you can see that the air flow rate is much more disturbed by the pressure of the pressure controller. This doesn't affect the liquid flow rate because of the compressibility is not the same for the liquid and the air. So we did have to, like I said in the slide before, like we said, we did have to implement some kind of signal processing by the modeling and by the regulation to understand, to just deduce the liquid flow rate, the liquid behavior from the air flow rate. So on the left, you see a lot of peak, you see a lot of noise due to the pressure change because we have the pressure control for adapting to the flow rate the customer wants. And on the right, you have the result of all the modeling and the algorithm we have implemented in our software and the firmware of the NIFS in order to ensure that the air flow rate that we show, it is equal to the liquid flow rate. So just to finish, you can see on the right that the gray curve and the orange curves are fitting well. And this was the goal of the development.
Okay, so thank you, Nicolas. So yeah, I wanted to go more into details with some results that we already have today. We have a technical note. I will show you more into details at the end of the webinar. I will show you the link, the URL link of the technical notes. But we made actually two tests here, two simple tests, flow rate steps, so ranging from 100 to 600 microliter per minute, so going up and going down. So here's that's the typical curvature you can obtain and you can achieve with the NIFS. So I wanted to emphasize and check more into details on the first flow rate measurement we are making with the system to show you how the system works in general. So the algorithm is based on a learning phase. So this learning phase actually learns the microfluidic resistance of your system. So how does it proceed? So we are trying to achieve one flow rate. And we can maybe have a zoom on the first measurement. So we are trying to achieve one flow rate. So the system is trying to go to one flow rate. So first of all, what we can see here is that in green we have the regulated pressure, and in blue the regulated flow rate with the NIFS. And so at the first step on the first implement, we are trying to achieve 100 microliters per minute. Is trying to achieve this flow rate. So there is this step in which we are trying to achieve the 100 microliter per minute, and then we have a sensing part because we are measuring flow rates every 10 seconds in average. So this is the actual value that we measure with the NIFS, and then since the NIFS knows the flow rates we have achieved with the implemented pressure, he will know what is the next pressure to apply in order to have the right flow rates that we ordered. So it's basically based on the fluidic resistance of your system. So the resistance of your system depends on both the pressure and the flow rate, and so we can determine the resistance of your systems out of these two parameters. And then after this first test or the first learning phase, it will be way smoother for the system to reach the right flow rate directly. So as you can see on the different steps. So once he knows what type of pressure needs to be applied to reach a specific flow rate on your system, it will be pretty straightforward to the NIFS to reach for the other values. And so this is what you can see here with the different steps directly going on the right flow rate, targeted flow rate. So this is what I wanted to mention. So for the first order, maybe it takes about 30 seconds to reach the right flow rate in your system. And then we will have a way higher response time for the next orders. So I will mention some typical applications, but for instance, if you have if you have a stable flow rate injection, it's pretty convenient. The system is a right fit with your system, but if you have like flow rate changes every 1 second, it may not be the perfect fit. So regarding flow rate stability, that's a very straightforward experiment. So we just put 200 microliters per minute for more than 10 minutes, and we just measure the average and the standard deviations, which are in fit with our performance and our specifications. I also mentioned that the flow rate range ranges from 100 to 10 milliliters per minute. It is still possible for you to use it below 100 microliters per minute, but we do not ensure the same specifications. We do not ensure the 5% accuracy, for instance. And for instance, when I made an experiment at 50 microliters per minute, I reached an average of 52.4 microliters per minute with a standard deviation on 2.8, sorry. So it's a bit slightly above 5% accuracy, but it can still be good enough for some of your applications. So that's up to you. That's up to the performance requirements you need and what the flow rates you want to achieve. And so yeah, finally, you have seen the product, you have seen some performances, but let's see how the whole system looks like. So here it's just a few snapshots of how we connect the whole system. So here you are seeing the FOEM that we connect to the NIFS flow sensor that is connected to the FOEM directly. So then it's only pneumatic tubing connected to the reservoirs, and we also added a flow sensor to make the comparison between our calorimetric flow sensor and our NIFS. So as you can see here, maybe I would just go back to the whole system. You have the FOEM here, which is the pressure controllers for OEM with the pressure module directly connected to the NIFS and connected to the reservoir. And then the air pushes, so thanks to the pressure on the control pressure, air is pushed onto this reservoir, goes to the flow sensor, to the calorimetric flow sensor, and then out of the sensor. So of course, it's just a presentation system. If you're using the NIFS, you will not need to use the thermal flow sensor, of course. But this is just to make the comparison, to make sure that you understand that we have the same flow rates, even if it's maybe not very intuitive for you, that measuring the gas flow rates is like completely equal to the liquid flow rates. And so this is our interface. So here we will directly go to the right flow rate because we already made a learning phase here. But this is how the system will behave in general. What's important to note here is that that's our end user interface. It's also can also be used with our dedicated SDK. So we have a complete SDK with some functions that you can see more into details when you go through our webpage to make your own regulation and to integrate part of our regulation into your complete system. So yeah, well, maybe I can go through another step. And yeah, so what's also interesting here is that there's maybe sometimes a slight difference between the two systems. So two reasons. The one is that the first one is that the NIFS will also make a few increments in order to reach the perfectly right flow rates. So it will be some adjustments throughout the time. And also, of course, if there is like a slight difference between the NIFS and the thermal flow sensor, it's because they both have different technology to measure the flow rates, and we have, of course, different type of technologies, and there's like 5% accuracy on one, 5% accuracy on the other, and in the end, it's not a perfect match, but it's still very, very similar. So I think you understood the working principle of the system and how the system look like. This is I wanted to finish with a comparison of the flow sensors that are available on the market today. So each of them have, as I said before, pro and cons. So that depends on your application, what you're doing, what you want to put the best effort on. Is it invasiveness? Is it a no-go for you to have a flow sensor on your fluidic line? If it is the case, the non-invasive flow sensors might be a good fit for you. Also, the flow rate ranges, the pressures that can be used, the response times of your system, as I said before. There's like a difference between the reading, the regulations, and also the accuracy. So if you want to have a very responsive, highly responsive system, you might want to opt for a calorimetric or caloric flow sensor. If you want to opt for a non-invasive flow sensor, or like if you want to use different type of liquids, you want to opt for the non-invasive flow sensor. And also there's also prices to take into account. So as I said before, Coriolis flow sensor is about 10 times more expensive than a calorimetric or non-invasive flow sensor. Yeah, so I wanted to finish with the typical applications where the NIFS finds its use. So today we have a lot of customers that are interested into using this system for biological applications. It makes no doubt, of course, because they require a completely sterile environment. And also droplet microfluidics, but still droplet microfluidics for biological applications. So of course, for long-term cell culture and perfusion, that's a very good fit because as it's not on the fluidic line, it ensures stability in the long term. So if we're making a measurement for 24 hours, 1 day, 2 days, the flow sensor will never be in contact with your liquids. So it usually reduces the risks of having some failure into your systems over time. Also, we have a few customers that are using the NIFS for making droplet-based microfluidics. So they're basically for biological encapsulation. So that can be for bacteria, cells encapsulation, in which again they're using biological solutions, and they don't want these solutions to be in contact with any kind of non-disposable flow sensors. So they are really willing to use this kind of sensor. And then, yeah, of course, sample preparation for cell cytometry, blood testing. Of course, you don't want to use blood into your flow sensor, otherwise you need to clean it. It's very dirty and complicated to clean. And drug screening also applications. So as a conclusion, so the non-invasive flow sensor is a very unique sensor on the microfluidic market. It's the first sensor that is completely non-invasive, which makes it very reliable and versatile because you don't need to make a calibration depending on the liquids. It gives overall great performances. So we have similar accuracy compared to the flow sensor, and it's well suited for biological applications. So we discussed the main challenges we had during this development. We are still considering we're investigating making another version for lower flow rates and for multi-channels, and that will maybe be the next steps of our developments. If you want to have more information about the NIFS, you can go through the NIFS webpage, in which you will find the general information, the datasheets, and usual manuals, and some videos as well. The technical note I've discussed a bit, so it will be more detailed, of course, in this technical notes. Also, we have a review on the technology of the system, which explains how the technology works more into details. And finally, we have a very nice review that explains all of the flow sensing technologies that are available for microfluidics. If you want to have a complete overview of all the flow sensors available, that's a very good review. So thank you for your time. And I and Nicolas will be more than happy to answer to your questions. So I think there's already one question here. So, okay, so the first question is the gas compressibility taken account? What is the range of the pressure that the sensor is applicable? So I think that has been already discussed by Nicolas, but maybe Nicolas, you want to take this question again?
Yeah, for sure. Just the second question is the simplest one. So the range of the pressure that the sensor is applicable is from 0 to 2 bars. And we compensate the volumic flow rate for this range of pressure. And the first question, so about if we take into account the compressibility of the gas, yes, we do by modeling of the transient response of the gas flow rate, the air flow rate. This has been one of the challenge. So we don't take it in account like there's a parameter in the model, but we do identification, characterization of the transient of the peak of the air flow rate during this transient, in order to deduce as quick as possible the real liquid flow rate. We do have a model in our algorithm to reduce this time of transient. We don't reduce physically the transient response of the air flow rate, of course, but by the modeling, we can deduce what is the liquid flow rate during this time.
All right.
I'll let you know, and I can.
Yes, thank you, Nicolas. So if it's clear, let us know if it's clear or not. So next question is it compatible with nitrogen, air, or other gases? So it's compatible with air, and then it's also so the trick here is that it's of course calibrated. It does need calibration on the liquid parts, but of course there are sensors that are calibrated on the pneumatic part. So it's calibrated for the air. And for what's interesting here is that the properties of the gases change a bit less, have a less impact, less important impact on the measured flow rate compared to the liquids in terms of properties. Maybe Nicolas, you can elaborate this question regarding nitrogen. I'm not sure of this one.
Yes, so the answer is yes, it is compatible. The only thing is that the density of all the gases are different, so we need to apply a correction parameter to the measurement.
Yes, yes, and also just of course it's not compatible with corrosive gases, but yeah, regarding nitrogen, air, it's compatible. Yes, as Nicolas said, the density of the air changes, but it has a less impact on the measured flow rate compared to the liquid. So for instance, we know that for our calorimetric flow sensors, changing the thermal properties of the liquid have a huge impact on the measure flow rates. That is a bit less the case for gases. But we can definitely make a calibration for you if it's required. So next question. If we are using a compliant system and the resistance is changing with pressure, the NIFS can be used in such environments. I'm not sure I understood completely, but if you're mentioning that the resistance of your system is changing over time, the NIFS can be used, of course. That's actually why it's interesting to have a flow rate regulation and not only sensing. We apply a flow rate, and then it will measure the difference in the differences in flow rate because of the resistance changes, and it will adapt the pressure to keep the right flow rate. I'm not sure if it's if it was your question or not, but please tell me if it was not clear.
Maybe I can add.
Yes.
Yeah, maybe you can clarify the question. But for example, if you mean that sorry, the liquid is Newtonian and the pressure is non-linear, it will work, but then it's a trade-off of our algorithm. Our algorithm works very well when the curve pressure flow rate is linear. It's easy for the algorithm because it's based on inner learning. It's easy for the algorithm to know what will be the pressure for the next step or when you need to change the flow rate. So when this characterization between pressure and flow rate is not linear, it's a little bit more complicated for the algorithm to find the next good point to adjust the pressure. So in such case, then it is a trade-off with the response time you need. But there's no issue that the algorithm will find the good pressure for the flow rate you need.
Okay, so you mentioned that can be used for droplet microfluidics. Did you already test it if the response time is compatible with that? So it's compatible with droplet microfluidics. So here, what we will recommend is using one channel with the NIFS. For instance, with the liquid you're using, the biological liquid with the NIFS, and the other with another type of flow sensor. For instance, for the liquids that are not biological, you're using another flow sensor. So if we used it for droplet microfluidic, the answer is yes. So we made a custom development for a specific customer that wanted to generate droplets for encapsulations, and we are using the NIFS inside of it. As a standard product, it will maybe depend on your specifications. It will depend on what type of microfluidic chip you are using, what kind of flow rates you are using, and also the response time you need, because for instance, if you take a syringe pump to reach the right flow rate, sometimes it takes about 30 seconds, 1 minute to reach the right flow rate. So it started to push and then it will reach the right flow rate. With pressure, usually you have a very higher response time, but with the NIFS, the response time is a bit degraded. So it's a trade-off. It will take about, as we said before, 10, 30 seconds to reach the right flow rate. If you want to generate droplets for, say, 10 minutes, it's completely relevant to use the NIFS. If you want to just generate droplets and change the size every 10 seconds or things like this, it might be not completely relevant. Next question, is it compatible to all your pressure regulators portfolio? So today, the NIFS is available for OEM products. So which are the pressure controllers, which are the PX, the PX, the POEM, and the FOEM. And we are considering developing a similar product for the research market. Will it be interesting for you? We're still evaluating if it's could be useful for the research market, so including the Flow-Easy and the MFCS and so on. Maybe it would be interesting if you can be in touch with us, maybe like contact us on contact@fluigent.com or contact just on my personal email address, and we can discuss your project and see if we can find use for your use, because I'm not sure if it's if you're mentioning the Flow-Easy or if you're mentioning the FOEM, but today it's for OEM products. Able to measure positive and negative pressure. That is correct. I think we did try it once. It worked well. Yes. So yes. Maybe Nicolas, you can confirm that, but we made the test, right, with the negative measurements.
Yeah. I guess it is in order to induce a negative flow rate, maybe, or maybe not. I don't know. But yes, the sensor can. You can apply negative pressure to the sensor, to the NIFS, and the NIFS can also sense negative flow rate.
Yeah. Actually, if you put the NIFS on the wrong direction, it will measure it oppositely. Okay. Any other questions?
Yes, because I think there's a question from Abbas.
Yes.
Concerning the Flow-Easy, maybe, and the FOEM.
Okay. Yes. Is it an obligation to work with your equipment, tubing size, and fluid container? So it is done to be used with our pressure controllers, definitely, because the whole algorithm that we made, the whole signal processing that we developed, was developed for our pressure controllers. And also regarding the tubing, it's not an issue, but regarding the reservoir, you will also need to use ours, because we also developed completely leakage-free reservoirs, in order there's no leakage on the whole gas system. So if you're using different type of reservoir, that can be an issue for you. You will have leakage, and it will affect your measurements. So from the pressure controllers to the reservoir, it has to be with us. And then tubing, cheap, anything after the reservoir, it's up to you. You're welcome, Abbas. So are there other questions? So if there are no any other questions, I would like to thank you for your participation. You will also be able to reach me with a Calendly meeting next week and the next 2 weeks. If you want to have a personal presentation on the system and maybe a live demonstration of the system. So we will provide to you my Calendly, and you can book a meeting with me next week, and so that we can discuss some more into details on your requirements with the NIFS. Also, feel free to contact us at contact@fluigent.com, marketing@fluigent.com, or on my personal address, bruno.charletti@fluigent.com. So thank you for your time, and thank you for your participation.